and welcome back, students. Today we get to discuss optimization, and we're going to start by looking at the different levels of optimization. So, optimization. Let's start by asking first, what is optimization? Well, in computer science, software optimization is the process of modifying software to make an aspect of it work more efficiently or use fewer resources. If you recall our lessons from Big O, a computer will either focus on time or memory allocation. Can't really do both. Like, you can try, but always something has to give more than the other. So, for example, if memory is a premium, like you don't have a lot of storage or onboard memory, then the program may choose a slower algorithm that's going to use less memory. All right, let's talk about those levels of optimization. Now, this optimization process occurs at different levels. Higher levels have a greater impact and are more difficult to change further you are into a project. So therefore, performance is often part of the specifications of the project. So when you start talking about time and speed and all that stuff, it's all part of it. So for example, a video game with 60 frames per second is pretty acceptable, and it's like the standard. But if you have something like 6 frames per second, that's unacceptably choppy. Like, nobody's going to play your game at 6 FPS. Now let's look at some of the different levels of optimization. The first one is the design level. This is the highest level. Design is optimized to make the best use of available resources, given goals, constraints, and expected use or load. The architectural design of a program overwhelmingly will affect the performance. So more than anything else, design is very important because it'll change how you do everything else going here forward. And the choice of the design is dependent also upon the goals of the application. This is also when you make your platform and programming language choices at this level. So if we're talking the goals of the application, let's say it's to make a video game. Okay, so that's your goal, make a game. What platform do you want that on? Do you want it to be a mobile game? Do you want it to be PC only? Do you want it to be Xbox? Do you want it to be PlayStation? What's your goal? Once you decide that, then what programming language you're going to construct in? Is it going to be in C++? Is it going to be C#? Lots of choices to weigh on in the design level. The next thing you look at are algorithms and data structures. This is the next level after a good design is to make a good choice of algorithms and data structure. After the design, this affects efficiency more than anything else. Generally, your data structures are more difficult to change than your algorithms, as a data structure assumption and its performance assumptions are used throughout the program. So when we start talking about data structures, that's things like, for example, hash tables, binary trees, those kind of things that are used versus algorithms, which are just the actual different pieces of the code that you might be using. Now those algorithms, this primarily consists of ensuring that algorithms are either constant, so that's your big O1, logarithmic, big O log n, linear, big O n, or in some cases log linear, that's n log n. So those are the kind of structures that you want to see. You don't really want to look at something like quadratic or cubic or anything like that, because it just becomes runaway and it's not really anything that's really good to address. So we really try to stay away from polynomial type functions. The next level is source code level. Beyond general algorithms and their implementation on the abstract machine, concrete source code level choices can make a significant difference. Some optimizations are performed by optimizing the compilers. This depends, of course, on the source language, the target machine language, and the compiler. And both can be difficult to understand or predict, and they often change over time. This is also where the understanding of compilers and machine code can improve performance. So if you have a good understanding of machine code and how that works, great. It's a lot easier for you to look at the source code and figure out what you need to optimize. The next level is build level. Between the source and the compile level, directives and build flags can be used to tune performance options in the source code and compiler respectively. Using preprocessor commands to disable unneeded software features, optimizing for specific processor models or hardware capabilities, or predicting branching. So this is where it's like, hey, certain CPUs are going to be used on certain machines. You can take advantage of those different features for optimizing. Short-space software distribution systems can take advantage of this form of optimization. The next level, of course, is compile. This is use of an optimizing compiler tends to ensure that the executable program is optimized at least as much as the compiler can predict. So the compiler will look and say, hey, you can optimize this. It will give you suggestions. Next is the assembly level, which is our last level here. This is the lowest level. Code is typically written using an assembly language. This is designed for a particular hardware platform that can produce the most efficient and compact code if the program takes advantage of the full repertoire of machine instructions. Many operating systems used on embedded systems have traditionally been written in assembler for this reason. Now, we're not talking like Windows, that's not embedded, but when you start talking like embedded software, they have their own OS that's in there. Now, programs other than very, very small programs are seldom written from start to finish in assembly due to the time and cost involved. From the little bit that you guys have done with the LC3, you will have a good understanding of like, would you really want to write all your code like that? Instead, what happens often is most are compiled down from a high-level language, such as C, to assembly and hand optimized from there. So they'll write it in C, they'll very much convert over to assembly, and then they'll look at the individual optimizations from there. With more modern optimizing compilers and the greater complexity of recent CPUs, it's actually a lot harder to write more efficient code than what a compiler can generate. And few projects really need this ultimate optimization step. So the assembly level step is not as used as often now. And as such, much code written today is intended to run on as many machines as possible. Like, you're not targeting a specific machine, you're targeting a general group of machines. Like, you might say, hey, I'm going to want this to run on all Windows devices that run Windows 10 and newer, or Windows 8 and newer, something like that. Or you would have, maybe you're targeting mobile devices and you want to run a certain version of Android and newer. That's the kind of thing. You're not going to say, I'm going to run for the specific model that's going to run the specific OS, that's going to have a specific chipset. No, instead you're doing more broad stroke because you can hit more targets into market. As a consequence of this, programmers and compilers don't always take advantage of the more efficient instructions that are provided by newer CPUs or taking advantage of the quirks of older model CPUs. So there is some drawback to not being able to do this. All right, but that concludes our notes, folks. Until next time.